This is a chip manufacturing tool. This is the biggest molecular beam epitaxy tool in the world, as far as we know. And this tool is making a very special material that we need to realize any kind of useful quantum computer.
California-based startup PsiQuantum is one of the many companies working to make large-scale quantum computing a reality.
We are inside the Stanford Linear Accelerator cryo plant that makes liquid helium. And PsiQuantum is using a little bit of that helium. And what we do is we load chips into this cabinet to cool those chips to very low temperature. So this is minus 270 degrees Celsius. It's about 2.3 Kelvin base temperature, which is the same temperature as deep space.
Quantum computers promise to solve problems that are impossible for traditional computers, with the potential to transform entire sectors, including material science, pharmaceutical research, and financial services. Investors have also been bullish about the technology's future, with some quantum computing stocks rallying over 1,000% in 2024.
If investors are looking for the next big jackpot, it sounds like they're really focusing attention on quantum computing stocks.
Excitement around quantum computing reached a fever pitch after Google announced its Willow quantum chip at the end of last year.
By our best estimates, a calculation that takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years, or a timescale way longer than the age of the universe.
Since then, a slew of other announcements from other tech giants have sustained that hype around and investment in the technology.
Microsoft announcing what it calls a quantum computer breakthrough with its new Majorana 1 chip.
Amazon jumping into the quantum computing race with its first chip.
We're going to open a quantum research lab in Boston. It will likely be the most advanced accelerated computing hybrid quantum computing research lab in the world.
Intel and IBM are also working to develop quantum technology, as are governments and numerous startups. The United Nations has even proclaimed 2025 as the International Year of Quantum Science.
It's a new class of computation that I think can dramatically change most aspects of industry, commerce, and science.
By some estimates, greater than $50 billion have been pledged to quantum technologies, of which quantum computing is one, by governments around the world.
Despite massive advancements in the field in recent years, right now, these quantum computers are not able to solve the big real-world problems. It's still more theoretical. CNBC visited one Silicon Valley startup to find out how close we are to having a useful quantum computer, and spoke to experts about the major challenges this tech still faces as engineers work to transition it from lab experimentation to commercial viability.
So hopefully they'll cover this soon. But one of the key distinctions here for a quantum computer, and generally what it means, is that usually you're operating on, I believe, some type of particle instead of like a standard chip or something along those lines. And so it is fundamentally different in how it operates compared to standard computers today. And so they're going to be operating on things that are much smaller. And also, I believe that there's different properties of that. I'm not an expert in quantum computing. Maybe I should be, based off of some of these growth rates for these companies. But the key idea is generally you're going to be able to have much smaller chips, or chips that can do a lot more things than what we have today. And that a lot of what we use in the computer science space sort of assumes that quantum computing is like the holy grail of computing. Like that is the peak of what we'll be able to accomplish. Maybe someday there'll be some type of like physics or some other chemical breakthrough that allows us to consider something else. But at least since I've been in computer science, this has sort of been touted as the best possible scenario. Whereas existing chips today, we're continuously advancing them, and that we always expect there to be a better version of what currently exists, but it's on a whole other realm. So hopefully they'll cover it a bit more, and I'll give them a few moments to do so. Otherwise, we can probably discuss that a little bit more.
The theory of quantum computing has been around since the 1980s, when physicists first suggested that quantum mechanics could be used for computation. By taking advantage of quantum physics, quantum computers are able to produce huge leaps in processing power and solve problems that conventional computers simply cannot manage.
There are two really important special quantum mechanical properties that give quantum computers an advantage on classical computers in solving certain types of problems. The first is called superposition. The second is entanglement.
Unlike classical computers, which store information in bits, with each bit representing either a 1 or a 0, quantum computers use quantum bits or qubits, which can exist in superposition of 1 and 0, meaning they hold multiple possibilities simultaneously. Qubits can also be entangled, where the state of one instantaneously affects the other, no matter the distance. These properties enable quantum computers to solve certain types of problems exponentially faster than classical systems.
So that's interesting. I'm glad that they were able to elaborate on that. I knew that there were other criteria for it. I'm not entirely sure off the top of my head the entire point of superpositioning of a bit here. I think the immediate reaction I would have would be that this allows you to store maybe like a float, like a decimal type value within what is currently considered a bit on computer science, which again is either just on or off, a 0 or a 1. And so that is one application that could allow for things to potentially be faster, but I'm sort of doubting it, at least at face value. And I would say if anyone's actually into quantum mechanics or into quantum computing and knows better than me, feel free to post that in. But that would probably be the immediate reaction that I would have, which is instead of you storing multiple bits at the same time to represent a number, then you could just potentially use a single qubit and then have the like superposition of that to represent a fraction, for instance, or a decimal. But that would generally be a trade-off for memory, so that would allow you to have potentially larger problems or a larger problem space that you're solving towards. This entanglement piece, though, that does sound very interesting for computational power. So there's a lot of times where you want things to be updated automatically, and you manually go through that process of changing certain values based off of other values. And so for these things to happen like instantaneously under the covers without like software necessarily in this scenario doing it, then that certainly would speed things up, because then you could reduce the number of operations you're performing, because some of them are just inherently happening with the medium that you're computing on. And so that certainly sounds like that could be a huge advantage. Another reason why the superposition one would enable for something that could be a little bit faster is we do have issues where there's a limitation on how much memory exists. And so you might have to break a problem up into multiple chunks. And so, for instance, if you could take a single qubit and then use what maybe like 8 bits or 16 bits is used for today, then obviously you can have magnitudes larger problems and data that you're processing at a particular time instead of running it in sequence or even trying to go through multiple passes. So those are certainly some advantages to it. And I think the other obvious advantage is the amount of space that it takes up. So a bit on a computer chip would take up a sizable amount of space in comparison to these qubits or like these particles or whatever these are. So that would allow you to have a lot more computing real estate than you would otherwise.
Unlike classical computers, quantum computers can directly simulate that behavior. And that allows us to design things instead of just discover things. All our drugs, we've gone into the Amazon, we've pulled bark off trees, we've seen how many mice die, and we've tried to make an oncology drug just by guessing and trying to optimize around stuff we discover. But being able to design materials directly, to be able to design chemistry, drugs, catalysts, requires a tool where we can simulate nature, and quantum computers are the first ones that can actually do that.
Quantum computers could also help with agriculture.
The way fertilizer...
I'm not really sure what that individual was referencing. I'm going to try seeing if I can kind of go back to his intro here. So he's a co-founder and general partner at Playground Global. Not really sure what that means. I'm not entirely following his argument of you can design these things directly. I'm not sure exactly what he's implying here. Again, this is where, for most intents and purposes, while quantum computing does unlock new features, how things operate are still going to be pretty similar at the end of the day. Like, math still has to happen at some portion, and then that math generates other things. It's not like quantum computers are not like inherently artificial intelligence or something like that, where like you could just ask it to do something and it's going to go do it. I think the distinction here is likely, again, how much you can put onto a quantum computer compared to a normal computer. So maybe you can do more rigorous simulations than you could otherwise, like having a variety of genomes or other things on there to like go through and select through and test and validate a variety of things. But he said that pretty whimsically, in my opinion. So he didn't come off as an engineer, in my opinion. So he might just be kind of hyping up this as a technology more so than an actual feature set that quantum computers enables.
The way fertilizer is produced today comes at a really steep cost for companies. They're spending about $100 to $300 billion a year, and for the environment. 3 to 5% of the world's natural gas is annually used for fertilizer synthesis. Scientists today know how to use computers in order to find a much more energy efficient alternative. The problem is it would take even the fastest supercomputer 800,000 years to
see. This is what I was sort of referencing in the previous example, which is the thing that it would enable you to do is take something that is infeasible today and do it faster than you would in current scenarios. And so that's where, like, you know, if you want to run an analysis on like every chemical compound that we know of in human history, then like that's going to take you a while, likely, especially if you want to do a number of variations, etc. And so like this would maybe speed that up so that it becomes a feasible thing that you do. But it doesn't just like unlock this like magic that occurs and you just say like, please give me one new genome, and then it just plops it out.
simulate all the maze-like molecular interactions of the key catalyst. With a quantum computer, it could be less than 24 hours.
But quantum computers will not replace conventional computers for everything. Some sectors could benefit more from the technology than others.
It won't replace AI. They are complementary technologies. Anything that is large data and small computation is not advantaged by a quantum machine. Optimization problems, physics problems, how we design fusion reactors, how we design superconductors, how we explore this incredible design space. Think of the most extraordinary applications.
Analysts estimate that the four industries likely to see the earliest economic impact from quantum computing are mobility, chemicals, financial services, and life sciences, which stand to gain up to $2 trillion in value by 2035. PsiQuantum says it's already working with a number of enterprise partners to experiment with potential use cases.
We're working with a bunch of different companies. So Boehringer Ingelheim, for instance, a large European pharmaceutical company, Mercedes-Benz, Mitsubishi Chemical, and various other Fortune 500 companies as customers and partners. They're working with us today with the hope that a quantum computer will allow them to design drugs, materials, fuels, catalysts, and really give them a new level of mastery over chemistry and physics that they hope will give them a profound competitive advantage in these areas.
Ironically, the same quantum properties that make quantum computers really good at processing complex problems also make the technology extremely difficult to work with.
Unlike classical bits, which are physically stable and robust, qubits exist in highly delicate quantum states, and these states are easily perturbed by even the smallest interactions with the external environment, things like thermal noise, electromagnetic interference, vibrations, acoustic noise. The other challenge is that quantum superposition is ephemeral. So superposition allows qubits to represent multiple states at once, but maintaining this state requires precise isolation from the environment.
Think of
So something I would correct here a little bit, which is, while I do agree with the sentiment that qubits would certainly be much harder to keep in a particular state to keep track of. What they're referencing was also a problem for computers in the past. So going from like analog to digital exists, and also they don't ever exist perfectly at one thing. That's not how the physical universe works. And so while we think of them as perfectly on or off or 0 or 1, there's actually a certain amount of current, and that there is fluctuation in that current for computers today, but that we use thresholds in order to understand which one it is. And we assume that once it's above a certain threshold, that it means that it is on, and once it's below a certain threshold, that means that it is off. And so again, this isn't, I think they misrepresented how this works. And so for me, the way that I picture it is more so the difficulty that we likely had 50, 60 years ago, or maybe beyond, for thinking about computers and processing and chips in general. They had to worry about these things too, even for a digital space. And what we currently consider like a no-brainer problem that is just so obviously stable wasn't that stable for them at the time. That's what took time to advance and progress on. And so I suspect this is going to be true here as well, which is this is a very challenging problem. If it was easy, we would already be doing it. But eventually we'll get to the state where we've learned enough about doing this and we've gotten so good at doing this that, again, we'll think that's just easy. That's how computers work. It's just how it is. You have qubits. They exist. You prevent interference from external sources, and they just work. Like, we won't give it much thought. And maybe there'll be another problem that exists later down the road from some other breakthrough in physics that allows us to consider a different type of computing.
Coherence as a way of keeping a quantum system stable so that it can run calculations.
The whole difficulty of constructing a quantum computer is making something that, on the one hand, cannot interact with anything, right? On the other hand, you can control it. But controlling it means it's interacting with something, right? So it's like this very, very difficult engineering problem.
Quantum companies have been experimenting with different quantum technologies, each with its own drawbacks and benefits.
There are superconducting qubits. There are neutral atom qubits. There are trapped ion qubits. And then there are other qubits which you see a little bit less industrially.
Google, IBM, Amazon, and Rigetti Computing are all betting on superconducting qubits, while Xanadu and PsiQuantum use photonic qubits. In February, Microsoft announced that it had created a quantum computing chip, Majorana 1, that uses a new type of qubit known as a topological qubit. The technology required the creation of a new state of matter that could make quantum computers more resilient to noise and shorten the technology's development timeline from decades to years. The sensitivity of qubits to external environmental factors also makes quantum systems very prone to error. For many qubit technologies, managing this error has meant having to keep quantum chips at extremely low temperatures.
The icon of quantum computing is the chandelier. That system is all about cooling these chips to very, very low temperatures. And so they have to run deep space temperature, liquid helium temperature, very, very cold.
Errors are also mitigated through the use of special algorithms that allow experts to correct errors faster than the machine can make them. This is something Google demonstrated with its Willow chip.
The Willow chip effectively operates below what's called the surface code threshold. Historically, when technology providers have added more qubits to the system, the overall system has a higher total error rate. What Google demonstrated is that with their error correcting code, adding more qubits to the system actually reduces the overall system error rate, and therefore there's a path to scaling with more and more qubits.
Peter Barrett, whose venture capital firm is a major investor in PsiQuantum, says that while Google and the other tech giants have made huge strides in quantum technology, he believes quantum computers based on photonic qubits, like the ones used by PsiQuantum, are more practical to scale.
Willow is the best quantum computer on the planet at the moment, but the machine PsiQuantum is making is 10,000 times the size of Willow. And the nice thing about photons is that they're much, much easier to keep isolated, and it's much easier to maintain the quantum state. And taking advantage of the fact that we have trillions of dollars invested in silicon photonics, in fiber optic cables, photons become a really strong candidate for building large machines, and their physics is well understood.
Part of that strategy, PsiQuantum is also moving away from the classic chandelier design of quantum computers in favor of a server rack design that you typically find in a data center.
Generally, the approach that we have here at PsiQuantum is that as much as possible, we want to build the quantum computer like a conventional computer, as opposed to a science experiment. And so we use regular semiconductor fabs, pretty normal chips. We use packaging that would be familiar to somebody from the semiconductor industry.
In February, PsiQuantum unveiled Omega, a quantum photonic chip that the company says contains all the components necessary to build utility-scale quantum computing. The chips are manufactured by New York-based Global Foundries. Another major barrier to scaling quantum computers is the lack of a highly technical workforce needed to design, program, and run quantum systems.
Currently, the talent pool is just far too small to meet the demands of the growing industry.
One way to overcome this talent problem may be by using more computers and leaning on artificial intelligence.
Yeah, that's an interesting problem to have because, you know, from having maybe like a IT specialist who manages a computer who just needs to know generally how to make sure computers are plugged in, that they're generally running under standard conditions, compared to maybe having like a physicist who needs to be there to understand quantum mechanics, who is potentially maintaining these machines. I actually don't know if it's going to be that extreme in some of these scenarios. But again, it does make sense that there's going to be a much larger scale for understanding on how these machines function in order to help maintain them adequately. And certainly it doesn't necessarily need to be all the way to like quantum physicist, but likely there's going to be a step up in knowledge and understanding that is required. I do like how that previous individual highlighted that they're actually aiming to make it more like what people are used to today, because that's what's likely going to help them win. If you have to retrofit your data centers in order to enable one of these quantum computers and it doesn't go with everything else that you have, those people might need to like invest in brand new locations, new setups, new training for people to maintain them. And so I do think the more you can make it like a standard computer today and be more hands-off and less finicky, then the more likely it is for adoption.
Already, we're using large language models. IBM, I think, was the first company to pioneer this in order to actually supplement developer knowledge bases and allow LLMs to program quantum computers, which I think will drastically alleviate the workforce upskilling challenge in quantum computing.
But it goes both ways. AI development could also benefit from quantum computers.
There are great AI tools that can help with designing some aspects of quantum computers. And once you have a quantum computer, you can produce training data to train AIs.
The potential of quantum computers to solve some of the world's hardest problems, like coming up with new drugs or materials for more efficient electric batteries, has many people excited. But it's challenges like this that have led some of the world's most influential technology pioneers to temper expectations about just how close we are to a useful quantum computer.
If you kind of said 15 years for very useful quantum computers, that probably be on the early side. If you said 30 is probably on the late side, but if you picked 20, I think a whole bunch of us would believe it.
Following Wang's remarks, the market was quick to react.
Shares of quantum computing stocks having a volatile start to the year after a steep run up in late.
Yeah, everyone's freaking out because they thought like quantum computers were to come like next year or something. That makes sense. But also this shows like how much hype can go into some technology. I feel like same thing happens with AI and blockchain and other stuff, is that people kind of run in having like a cursory knowledge of how it exists. They think this is a game changer, let me go all in, and not realize that there's actually a whole bunch of things that potentially hold it back from being like this silver bullet for all of humanity and all technology needs.
2024, many are now down double digits. In 2025 are concerns about just how soon the technology might be commercially viable.
We agree with Jensen, of course, that quantum computing is not here yet. And really the basis for his comments is that today there are small quantum processors. Google's system, for instance, that's about a 100 qubit system. The general consensus is that you need about 1 million qubits to really deliver on these world-changing applications.
At NVIDIA's annual Software Developer Conference in March, Wang gave quantum experts a chance to prove his timeline wrong.
This is the first event in history where a company CEO invites all of the guests to explain why he was wrong.
We think of ourselves as like 10 years, where you were 10 years ago. It's going to be another 10 to 15 years to get to where NVIDIA and all the other giants are.
But the complexity of quantum computing has generated controversy around some of the achievements in the field. For example, some experts and competitors are questioning Microsoft's topological qubits breakthrough that the company said would help it build a working quantum computer in a matter of years. Microsoft's research published in Nature in February, though the company said in an emailed statement that it submitted the paper almost a year prior, and during that time, Microsoft has made, quote, tremendous progress.
The exotic physics that Microsoft is pursuing is incredibly exciting, but it's a step along a journey that will ultimately yield something useful, but it's unclear when.
And for reference, I think for myself, these timelines are still pretty exciting. I'm trying to recall now, but I believe when I first heard of quantum computers, they were sort of referenced as like a future technology, like flying cars. Like it's probably going to happen someday, but like we might not see it ourselves, is how I believe it was referenced all those years ago. And so even if we have it in 10, 20 years, that'd still be way faster than I think what people were thinking about 10, 20 years before. And so there's a chance in 10 years these timelines are going to speed up, or who knows, maybe even in 5 years, these timelines will speed up when somebody has a particular breakthrough that's very helpful to this, that maybe they don't realize is on its way. And so I do still think that it's very exciting that these things are going to come to fruition and likely in my lifetime exist in some capacity out in the world, whether or not it's still a mainstream application or if it's just like a data warehouse where large companies like pharmaceutical companies or other just have large swaths of computing technology that exists that they make available to folks on standard chips or standard computers. But still, I think high level, this is still pretty quick. I'm not recalling exactly when we thought these were going to exist a while back. So even in the next decade or two would be pretty exciting, and especially so if it's faster than that.
Microsoft said discourse and skepticism are part of the scientific process and that additional data will be shared in the coming weeks. Although quantum computing may not be ready for prime time today, tangible progress is being made.
I do think there are going to be results this year that hint towards real quantum utility for commercial applications. Technology that started off as a quantum computing modality is now being used to make ordinary MRI machines 100,000 times more sensitive and allow them to directly image cancer metabolism. Technologies to see 2 kilometers underground to find the critical minerals for the energy transformation, that's already happened. And then the prize of the really big machines, the 1 million qubit machines, we know is only a handful of years away.
Public interest in quantum technology is growing. The number of quantum computing proof of concept enterprise projects surged by 50% between 2022 and 2024 to over 150 active projects. Consulting firm Booz Allen, Airbus Ventures, and Bosch Ventures have all invested in quantum computers. Meanwhile, Shadbolt says Illinois is investing $500 million to construct a quantum computing campus in Chicago, of which PsiQuantum will be the anchor tenant. PsiQuantum has also received $620 million from the Australian and Queensland governments to build a utility-scale quantum computer in Brisbane, which the company says will be operational by the end of 2027. Experts say investing now is a smart move.
When quantum computers reach quantum advantage, which is effectively the period in which quantum computers outperform classical computers at important real-world problems, it'll be much, much harder to get your hands on a quantum computer unless you're developing partnerships with the major providers right now.
Plus, Langione adds quantum computers don't need to be perfect to be useful.
We had practical implications for classical computers before classical computers were error corrected. Whether computers were doing atomic simulations for the Manhattan Project, they were doing important work for the Census Bureau. We think that there's a potential for the same thing in quantum computing. And candidly, we're even looking to the next 12 to 18 months for the announcement of the first example of industrial quantum advantage that would come before error correction. And then 2029 is when we think the real inflection could come in terms of massive value creation for end users in the right industry.
Shad Bolt is also optimistic.
You know, when I arrived in Silicon Valley 8 years ago, a lot of people, really serious technical people, told me that self-driving cars would never happen in my lifetime. Too complicated, too difficult. And of course, now every other car that we see in San Francisco is a Waymo. And so quantum computing has a similar sort of trajectory. What we're seeing now is a big leap to go from the small systems that we have today to the very, very large systems that are required for any kind of useful application.
Thank you for watching. If you've enjoyed what you've seen, please hit like or subscribe. I'll see you around.